Alright, in this video, I'm going to be talking about implicit differentiation, so let's get into it. To understand what implicit differentiation is, you kind of need to know the difference between implicit and explicit equation. So, explicit equations are kind of like equations and functions that we're used to. So, you'll have something y equals f of x. Here, y is the dependent variable, and x is the independent. Basically, your y is isolated, and it's some function of x. So this is explicit. Now, something we call implicit is basically neither of the variables is isolated. So for example, basically you'll have some function of both x and y on both sides. Or, let me just give an example. So like x squared plus y squared equal 1. That is an implicit equation, because all that it really requires to be an implicit equation is that your x's and your y's are not isolated. So you can solve for x and y, but as it is written, this is implicit. So the key idea here is that implicit equations are equations where neither x nor y is isolated. Alright, so now that you know what an implicit equation is, let's go through the steps of performing implicit differentiation. So I'm going to do this with an example, because I think it's definitely easiest to see just by doing it, kind of. So our function, or not really function, our implicit equation here is y squared equals e to the x minus e to the y. So the first thing we're going to do is differentiate both sides with respect to the independent variable. So the independent variable here for us is x, right? Because we want to find, in this case, we want to find dy dx, right? That's our goal. But to do that, we need to take a derivative with respect to x. So differentiating both sides with respect to x. Alright, so that is what that'll look like. Now, let's kind of carry this out. So basically, the next step is just to obviously simplify, but we're going to need the chain rule to differentiate these terms. And the reason the reason for that is, it might not look like it, but when we're differentiating y squared with respect to x, the inside is actually a function. It's y, which is a function of x. So let's just remind ourselves what the chain rule is. The derivative of, just say, f of g is equal to, what you do is the derivative of the outside evaluated at the inside, which would be g, so f prime of g, and then you multiply by the derivative of whatever's on the inside. So for us, that would be g prime. Alright, so for differentiating y squared, our outside function is x squared, because we're squaring whatever's on the inside, and then the inside is just y. So by the chain rule, we need to do the derivative of the outside function. That would be 2x, but we're going to replace that x with y, because y is our inside function. So 2 times y multiplied by, what's the derivative of the inside with respect to x? Well, that would be dy dx. So dy dx. And remember, this is what we want to solve for at the end. Alright, and then differentiating the other side, the derivative of e to the x with respect to x is just e to the x. And then for e to the y, we have minus e to the y. It's similar, because the derivative of e to the x is just e to the x, and we replace our input by the chain rule with the inside function. But then we need to multiply by dy dx, because that's the derivative of y. So basically, whatever functions have y in them, like y squared and e to the y for our example, you're going to have to multiply by dy dx on the outside because of the chain. All right, so the final step is because our goal is to find dy dx in the end, what we need to do is algebraically solve for dy dx. Now, I just like to note dy dx is the same thing as y, maybe I should write it red, y prime. So these are just differing notations, but they are the same thing. So I'm just going to write y prime because it's a lot faster to write. But basically, we need to solve for y prime, which is the same thing as dy dx. Or dy over dx. I keep saying dy dx. Alright, so rewriting with y primes, we get... Alright, so I'm going to add e to the y prime, to both sides. So on the right side, this minus and plus will cancel. On the left side, we can group our like terms. So we have a y prime, we can take out both of these. And then the rest would just be 2y plus e to the y. Okay, so what we have now is 2y plus e to the y, all times y prime, is equal to e to the x. So our goal here is to get y prime, so really we can just divide by all of this stuff. Oop, I don't know why I'm in blue. Okay, so if we divide by 2y plus e to the y from both sides, this would cancel out. What we would get is e to the x all over 2y plus e to the y. So, basically, just to recap, what we did is we had an implicit equation. We differentiated both sides with respect to the independent variable, which is almost always going to be x. And then we used the chain rule to aid in our differentiation. And then after we had all of our dy dx's and it was all simplified, we solved for that dy dx. So if I write it using the other notation, so now that we have kind of gone through an example slow and we've gotten underlying concepts, let's do some practice. Alright, so this one is evidently quite a bit harder than the first example. So what we have is x squared minus 6y cubed is equal to natural log of x plus y. And what we want is dy over dx. So, first thing, if we differentiate both sides with respect to x, we get 2x, because that's the derivative of x squared by the power rule, minus, so we're going to have a minus 6, right? So we can just pull that out of our derivative. The derivative of y cubed, well, our outside function is just x cubed. Our inside function is just y. So the derivative of x cubed is 3x squared. And then the derivative of y is y prime. So basically, the derivative of y cubed by the chain rule is going to be 3 times x squared, but instead of x, you replace that with y. And then times the derivative of our inside, which is y prime. So this derivative here is 3y squared times y prime. And then for the natural log of x plus y, our outside is the natural log. So using our chain rule, derivative of the outside is just, we do 1 over, we do the reciprocal of, and then place out the inside, so 1 over x plus y, times the derivative of x plus y. Well, the derivative of x with respect to x is just 1, and the derivative of y with respect to x is just dy dx. Or actually, let's write that with prime. So let's simplify a little bit. So 2x minus, so negative 6 times 3, that's minus 18. Y squared times y prime is equal to, let's distribute this 1 over x plus y. We get 1 over x plus y times 1 is 1 over x plus y, plus 1 over x plus y times y prime. Okay, so now let's subtract 1 over x plus y, y prime from both sides. Right now we're just kind of consolidating all of our y primes. So these will cancel. And then let's subtract 2x from both sides to get rid of this 2x, so we can just have, on the left, we'll just have all of our y prime stuff. Alright, so notice both this negative 18y squared, y prime, and this minus 1 over x plus y, y prime, both have a y prime in them. So we can factor that out. And the rest is just negative 18y squared minus 1 over x plus y, y prime. Okay, and then on the right side, we have 1 over x plus y minus 2x. Alright, so the final step is to divide everything by the stuff that's being multiplied by y prime. Alright, so writing with dy dx, what we get is 1 over x plus y minus 2x all over negative 18y squared minus 1 over x plus y. So we could definitely simplify this further. Let me just use parentheses to make it clear. We could definitely simplify this further. Multiply the top and bottom by x plus y to get rid of those fractions. But the goal is not really to practice the algebra of it, it's to practice the calculus. So this will be fine, though maybe your professor wants you to simplify this a bit more. Alright, next example. Alright, so for the next one, we have e to the y plus e to the x equals cosine of 2xy, and we want to find dy over dx. First step is to differentiate both sides with respect to x. So differentiating e to the y, our outside function is e to the x, and our inside function is just y. The derivative of e to the x is just e to the x, but we're going to replace that inside with y. That's our inside function, so e to the y. And the derivative of the outside is just dy dx. So let's use y prime. So y prime plus the derivative of e to the x with respect to x is just e to the x. Now for cosine of 2xy, our outside function is cosine, our inside is 2xy. So minus sine is the derivative of cosine. And then the derivative of 2xy. So we're actually going to need our product rule. We can factor out that 2, because we're just doing a derivative, and we can just factor out a constant. So this is actually two separate functions. We can think of this kind of like an f and a g. Well, the product rule tells us that when we differentiate a product of two functions, f and g, that's f prime times g plus f times g prime. Alright, so the derivative of x, which is our f in this case, would just be 1 times our g, which would be y. So 1 times y is just y, plus the derivative of g times f, or f times the derivative of g. So f is just x, and then the derivative of g is just y prime, because the derivative of y with respect to x is y prime. Okay. So now let's distribute all of this to these terms. Alright, so now let's consolidate all of our y primes and get those together. So, well, first, we're going to collect all our y primes on the left side. So let's get that e to the x out of here, because it doesn't have a y prime in it. So those will cancel. And then to get all of our y primes to the left side, we have a y prime on the right side, and it's subtracting. So let's just add this term. So plus 2x sine of 2xy, y prime. That will cancel. Alright, so now let's collect all of our terms with the y primes in them. So these guys both have a y prime. If we factor out the rest, we get e to the y plus 2x sine of 2xy. That's all times y prime is equal to negative 2y sine of 2xy minus e to the x. So the final step would be to divide by e to the y plus 2x sine of 2xy. So let's do that. Alright, so what we get when we divide both sides by that is our derivative, dy dx, is equal to negative 2y sine of 2xy minus e to the x all over e to the y plus 2x sine of 2xy. Alright, so I have one more example. It's a little bit easier than this, but I still think it's pretty cool, so I'm going to include it in the video. Alright, so the problem is we have this derivative of log base b of x, and we want to find it using implicit differentiation. So you might be curious how we would use implicit differentiation. Well, we were given that the derivative of the natural log is equal to 1 over x, or specifically, not just natural log of x, but the natural log of absolute value x is equal to 1 over x. You'll often see it written that just the derivative of natural log x is 1 over x, which is fine. We were given this, but we weren't really given, or I didn't explain the log base b of x, how to find that derivative in general for any base b, because the natural log, that's log base e. So in this example, I'm going to kind of show how you can use implicit differentiation to find the derivative of a log of any base. Okay. So we have our function, log base b of x, that's y. So we have y is log base b of x. Well, we know how to find the derivative of b to the x, of b to the something. That's just that b to the something times the natural log of the base, which would be b, so times natural log b. So how about we exponentiate both sides with the base of b, so this log cancels with the base, and then we'll just have b to the y equals x. Now, you might be able to see where implicit differentiation is handy here. We can differentiate both sides with respect to y, and we could find dx dy, but we're not really looking for that. If we differentiate both sides with respect to x, then we can find, let's just do it. Alright, so taking the derivative of both sides, the derivative of b to the y, well, we know that the derivative of some base to x, b to the x, is b to the x times times natural log of b. Here, we're going to place our x with y, because by our chain rule, we need to do that. So b to the y times natural log of b. But then the chain rule also says that we need to multiply by the derivative of y. Okay, and that's equal to the derivative of x, which is just 1. Okay, so we'll have, if we divide both sides by b to the y times natural log b, we'll get that our derivative is equal to 1 over b to the y times 1 over natural log of our base. Now, we have y, but we kind of want our derivative to be in terms of x. So, we already had over here that b to the y is equal to x. So, how about let's just substitute this in. So, we'll get that dy over dx is equal to 1 over x times natural log b. Okay, so this is our derivative. Alright, thank you for watching. I hope that you found the video helpful. Then please leave a like and subscribe. In the next video, I'm going to be going over logarithmic differentiation, and I think after that, I'm going to move on to some of the applications of differentiation, like curve sketching, finding maximums and minimums, just that sort of thing. So, anyways, yeah, hope that you have a good rest of your day, and thank you for watching.